Thank you. So is it live? Yes. Okay. So welcome everyone to this live session. In the Google Sheet, are you able to hear me? Yes. Can people hear me? Can people hear me? Yes. Okay. I was just requesting for a confirmation. Yes. Okay. So in the Google Sheet, which was shared with you, two people had asked, there were two questions. So I will try to solve those. So one of the questions was very interesting. So let me just write down that question. Tushar, shall I wait for a few minutes? Okay, one person is here. Okay, so the question was, consider the space, consider the topological space. M and R with the usual topology. Usual, or let's say standard topology. So I'm pretty sure that all of you know by now what this means. So M and R, the n cross n, the space of n cross n matrices with your entries that is being identified with R to the power n squared using the coordinates, and on this R to the n squared, we give the product topology. Okay, so and consider the determinant map. So I'll denote it by F. So this map is A goes to determinant. Okay. So and the question was, is F an open map? So there are two questions. Is F a closed map? And we will try to address both these. So this is a very nice question. This is a very interesting question because every time we learn some concept, we should try to test that concept on some of the important examples that we have. And when we look at n cross n matrices, one of the nice functions that we have on that is the determinant map, and therefore it's a very natural question. We have also seen these concepts about an open map and a closed map. So it's a very natural question. So we have this very nice map. So it's a natural question to ask. What can we say? Can we say something? Is this map an open map, or is this map closed? So it's easy to see that this map is not closed. So we call what is a closed map? So a map is closed. So let's say G of topological space X to Y is said to be closed if G of Z is closed in Y for every closed subset Z of X. Okay. So let's see that this determinant map, it's not closed. So for that, let Z contained in this n cross n matrices be the subset defined by the equations. So let's just take M2R. Let's take 2 cross 2 matrices. So here we have X11, X12, X21, and X2. Right. So we look at the vanishing of the equations. So we look at X11 equal to 1, X21 equal to 0, and so Z is equal to those. So that's and X12 times X22 is equal to 1. Okay. So from M to R, we have these three maps. So this is X11. Then we have X21. And the last one is we take X12 times X2. Okay. So under the first when we look at the first map and take the inverse image of 1, and we look at the second map and take the inverse image of 0, and we look at the third map and take the inverse image of 1. So all these three are going to be closed subsets, and when we take their intersection, that's going to be closed. So this implies that Z is the closed subset. Okay. So what does Z look like? So Z is like elements of this type. X11 has to be 1, so it looks like this. X21 has to be 0, so 0 here. And the product of these two, so we can let this could be any real number A, so this has to be 1. So let me write the argument. This is A. So A is. Okay. So Z is a closed subspace of MNR. And when we look at determinant of Z, it's, or let's say F of Z, yeah, F of Z is equal to the image of Z under the determinant map. This is exactly R minus 0, right? Because for each such matrix, the determinant is A, and A we can take any real number A. I'm sorry, A has to be, although A is in R, it has to be in R minus 0, right? Because otherwise 1 upon A will not make sense. So therefore, and we know that R minus 0 is not closed now. Since it's 0, it's not closed in R. This implies that F is not closed now. So it's not a closed map. So that answers the second question, and that's the easier one. So let's look at the first part of this question. So is F unputable? So I hope it is clear that F is not a closed map. That's fairly straightforward and easy. This is F an open map? That is more tricky. So the claim is that indeed it is an open map. So claim. Yes. It's So how do we prove this claim? So how do we show this? So what do we have to show first? So we need to show to prove the claim. We need to show that if U contained in M and R is an open subset, then f of U is open. Okay. And how will we prove this? So we have this is our U, and let's say this is the real line. Let's take a point A inside U, and let's say this is f of A. So we will show that there is a small neighborhood of f of A, which is completely contained inside f of U. So in other words, I will show that for every A in U, there is an epsilon positive such that the ball of radius epsilon around f of A is contained in f of U. Right? So this will show that f of U is open. So I hope the strategy of the proof is clear. So to prove this, we divide our proof into two cases. So let me go to the next page. So we divide the proof into two cases. Okay. So case one is a determinant of A, f of A, which is the determinant of A that is not equal to 0. Okay. So let's see how to prove this in this case. So in this case, so let us write. So let A be equal to, so we write it as a matrix A1, A2, AN, where AI is the ith column vector of A. Okay. So for this A, so we define an n cross n matrix, which we call B sub H, as follows. We take the first column to be 1 plus H times A1. The second column, we take it to be A2, A3, and so on. Okay. So let us see what is the determinant of A. So note that the first column is, so we have this rule. So determinant of BH is equal to, so the first column, we can write it as the sum of these two columns. So this is equal to determinant of A1 plus, sorry, determinant of A, or okay, we have multiplied the first column by 1 plus H. So this is just simply equal to 1 plus H times determinant of A equal to determinant of A plus H times determinant. So, thus, as H varies in minus epsilon by determinant of A, comma epsilon by determinant of A. In this set, yeah, so we get all values in this open neighborhood. Right. So as H varies in this set, this quantity is going to range from minus epsilon to plus epsilon. Okay, and therefore, when we look at these various BH, so we will get all values in this open set. Okay, and if epsilon is sufficiently small, or if H is, let's say, if H is sufficiently small, epsilon or H doesn't matter, then when we look at the difference of entries between entries of BH and A are small, right? Because if I look at the ijth coordinate minus aij, this is equal to 0 if j is not equal to 1, right? J is not equal to 1. Sorry. The matrices BH and A, they differ only in the first column. So let's look at the first column entries. BHI1 minus AI1. That is equal to H times A. Right. So if H is sufficiently small, the column A1 that is fixed, the column A1 is fixed, and so by taking H sufficiently small, we can make sure that all these BH, all these matrices BH are very close to this matrix A. So in other words, if H is small, then all the BH except H are in U, right? Because we have this U, and U is an open subset which contains A. So there's going to be a small neighborhood, small open subset around A, which contains all matrices whose entries differ from the entries of A by some epsilon small. Yeah. Right. So in the same, so therefore, so implies if so what I want to say is so I think we will get, so this implies f of u contains the set P so I'll take this. So let's assume that if h is strictly less than epsilon by determinant of A, then EH. So in view of the above discussion, we may choose epsilon small enough epsilon very small so that, okay, maybe I should have put absolute value of determinant A over here. So that if absolute value of H is strictly less than epsilon by the absolute value of determinant of A, then BH belongs to this open subset U, and this in turn will imply that f of U contains all contains the set epsilon. Okay, so this completes the proof in case one. This completes the proof when determinant of A is not equal to 0. Okay. So the case determinant of A is equal to 0, that is more tricky. I hope this is clear. Or yeah, if it's not clear right now, I hope at least the idea is clear, and then you can go back and look at it. And if you have more doubts, you can ask in the discussion forum. So let's consider the more complicated case, that is when case 2, the determinant of A is equal to 0. Okay. So here the idea is to, so remember that we have this open subset in which there is matrix A, right? So here the idea is that we will first replace A by a matrix A prime, which is again in this open subset. And so in this case, the idea is to first replace the matrix A in U by a matrix A prime in U, such that determinant of A prime is again 0, but now A prime satisfies a special condition, and the column rank of A prime is equal to n minus 1. So since the determinant is 0, so the columns of the matrix A, they are linearly dependent. So so we will find an A prime which is close enough to A, and therefore inside U, such that the column rank of A prime is n minus 1. So let's see how to do this. So first, so since determinant of A is 0, this implies that the rows, I'm sorry, the columns, I'll look with the columns of A are linearly dependent. Okay, so for simplicity, we will consider the situation where A1 can be written as a linear combination of the other columns. So assume that A1 we can write as some. So A, first we write A as these columns, A1, A2, AN. Yeah. And A1 we can write as C2, A2 plus C3, A3 plus C. Wow. So here the CIs are some real numbers. So, constants. Okay, these constants they only depend on the matrix A. Okay. So now let's write A as. Let's also write A as. So this A. So here, okay, here we have A11. Here we have A12 and so this can be anything. So here also. So this matrix, this n-1 cross n-1 matrix, let us call it C. Okay. And what we need to do is, so consider the polynomial g of t equal to determinant of C plus t times the n-1 cross n-1 identity matrix. Okay. So this is a polynomial of degree n-1, and so has at most n-1 roots in R. Okay. So choose epsilon very small such that epsilon is not a root of G of Q. Okay. And then we consider this matrix. So in particular, since epsilon is not a root of G of T, it follows that the determinant of C plus epsilon times this identity n-1 cross n-1 matrix is non-zero. That is, the columns are linearly independent. Right. Right. So now we consider this matrix. So now we are almost ready to define A prime. Right. So we consider this matrix. So let's look at this matrix. A12, A13, A14, dot, 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 up to A1n. And we leave out the first column. Okay, we leave the first column of A. So this is a n-1 and this is n. Okay. And here we have this matrix C plus epsilon times identity. right? So the columns of this n minus 1 cross n minus 1 matrix, this C plus epsilon identity n minus 1, they are linearly independent. So this implies that the columns of, so this matrix, let's call it M for now, are linearly independent. Okay, so that's an easy exercise. I'll leave it to you. So the columns of this smaller matrix sitting inside M are linearly independent, which means the columns of this larger matrix M, they are also linearly independent. And now we define A1 prime to be equal to, we take the same constants. Okay, so let's call this matrix M. So let's denote the columns by A2 prime. So A2 prime is this column. A3 prime is this column. AN prime. Okay, so we define A1 prime using the same relation. C1 A2 prime plus C2, sorry, C C2 A2 prime plus C3 A2 prime plus Cn. Okay. So okay, so let's make a few observations. So define the matrix. Define the matrix A prime to be equal to A1 prime, A prime to A. Okay, and let's make the following observations. Two observations. One, the column rank. These two observations are easy, and I will leave it to you to check. Of A prime is exactly n minus 1. And 2, if epsilon is sufficiently small, then the entries of A prime and A are very close to each other. Okay. So in other words, this implies that A prime is also okay. And this point 1 will imply that determinant of A prime is equal to 0. Okay. So now we do the same trick that we did earlier. So define. So we are in this situation. So in terms of a picture, we have this are U, this is A, and there is an epsilon ball around A inside U. And inside this epsilon ball, we have found some A prime. Right? So that determinant of A prime is 0. And determinant of A was also 0, right? So now define once again. So choose a vector. B0, which is not in the span of A2 prime to An prime. Okay. So this implies that determinant of this matrix, so we place V0 in the first column, A2 prime to An prime. Determinant of this matrix is not 0. Okay. So now define DH we define this matrix BH to be equal to A1 prime plus H times B naught, A2 prime, A3 prime. Okay. So then determinant of BH is equal to determinant of A1 prime, prime plus H times determinant of 0. Okay, so this is 0. This is equal to H times determinant of this thing, which is something not 0. Okay. So this is equal to H times some constant C, where C is not equal to 0. Okay. And once again, if H is very small, then PH is close to A prime. So if H is very small, then BH is going to be in some epsilon neighborhood of A prime, and therefore it is going to be inside this open subset U, right? And so this implies that f of BH is going to be contained inside f of U, right? But f of BH is what? It's just H times this constant C. Yeah. So as our H varies in some very small neighborhood of 0, we get that f of BH, it will vary in this scale by C, right? So this is, let's say, this delta. If H varies in this delta neighborhood of 0, then f of BH will vary in this C delta neighborhood C. So once again, this implies that f of U contains a small neighborhood of 0, which is equal to f of A. Okay. So in both cases, so thus we have proved that for every A in U, there is an epsilon positive such that the epsilon depends on A, of course. The epsilon ball around f of A is contained in, which implies f of U is open. So this implies f is new. Okay, so thank you. Are there any questions? Yes, this proof also shows that GLNR is dense in MNR. Thank you for this remark. And that's something which I think it does come in the course later on at some point of time. Yeah. So the proof is, I mean, it's not like a one-line proof. There are some steps and there are some reductions. Maybe there is an easier way to prove this. If any one of you knows an easier way, then please write me an email. Please share it with everyone in the discussion forum. But yes, so this proof, it has a few steps, and if you don't understand everything right now immediately, then that's okay. You could just go back and go through the notes or go through the video once, and it should be fine. Yeah, I think if you go through this proof, if you go through this proof and understand this proof, then you will benefit, you will learn something. Actually, in this proof, we use that GLNR is dense in MNR to show that GLNR is dense in MNR. That's like a very small piece of this proof. It's like a very small input into this proof, or the main idea which we use to show that GLNR is dense. Okay, so there was one more question which was asked in, I was requested to make some comment on that. And that was like, in general, how do we compute the path components of topological space? So there is no general recipe. Yeah, I mean, it depends on the space, and it's always a very interesting question. Uh, if if you encounter some space very often, it's a natural question to ask. Is this space connected? Is it path connected? If it's not connected or not path connected, then what are its connected components? What are its path components? So yeah, sometimes it can be quite difficult to answer these questions. For instance, uh, in the latest set of lectures which were released, uh, one of the lecture deals with proving that the special orthogonal group SON, that is connected. In fact, SON is also path connected, but to show that SON is path connected, we need some more machinery, which is not in the scope, which is beyond the scope of this course. It's not very difficult, but yes. So as you will see, like to already prove that SON is connected, we needed to use quite a bit of the technical um, ideas which we developed so far. So to answer the question, yes, there is no general recipe to find the path components of a given topological space. Uh, so given the topological space, we have to use our creativity to solve that problem. We have to find out. So I was asked, okay, this question. So what are the, so let me start this on new page. Okay, so this question about the determinant was asked by Akash Pradhan, I think, if I'm not mistaken. So thank you very much for this question. I really like this question. It's a very interesting question. So this next question, this is one of the assignment problems also, I think. Let U denote the space of upper triangular matrices in GL. What are the path components? So there is a question which asks, if we restrict the determinant map to GLNR, is it still an open map? And the answer is yes, because GLNR is an open subset of. So suppose we have f from x to y, and F is open. Now let U be open subset of X. Right. So we can look at the map F restricted to U and we can ask, is F restricted to U open? Right. And the answer is yes, because if we take any V inside U which is open, then since U is open in X, V is also an open subset, and U has a subspace topology from X. So therefore, V is also an open subset in X. So therefore, F restricted to U of V is equal to F of V. And since F is open, this is open. So this part is like very easy. Okay, so let me get back to this question. And let's solve it. So let's try to answer this question. So we define this following set. Let S be the set of diagonal matrices with diagonal entries plus or minus 1. Right. So for instance, if n is equal to 2, then S consists of these elements. So we have 1, 1, minus 1, 1, 1, minus 1, and minus 1, minus 1. Right. We look at all the other entries as 0. So we look at diagonal matrices such that the diagonal entries can only be plus or minus 1. Right. So the cardinality of S is therefore, so there are n diagonal entries and each of them can be plus or minus 1. So therefore the cardinality of S is 2 for n. Okay. So the claim is the path components of U. So U is the upper triangular matrices inside GL and R. Yeah. R in bijection with the elements of S. In fact, each element of S is an element of U. And yeah, so let's just go ahead with the proof. So first, we want to show that given, okay, let me just observe that S is a subset of U. So the proof of the claim will be almost immediate once we prove the following two, let's say, subclaims or assertions. Given any matrix A inside U, we can find a path. So it's always important in U, right? We always want to find a path inside U. Joining A. So let's see how to do this. A to an element of S. So how do we see this? So let's start with an A. So an A will look like this. So A is in U, so it's upper triangular. So we have 0 below. The diagonal entries are non-zero because our matrix is in GL and R. And then here we have this upper triangular part. So let's call this upper triangular part U sub A and this diagonal part D sub A. So then we can write A as D sub A plus U sub A. Okay. So now let's define this map from 0, 1 to U. this map is T goes to D sub A plus 1 minus T times D sub A. So now all of you should be able to easily check by now that this is a continuous map. So it should be clear to everyone by now. And let's notice what, so let's call this gamma. So gamma of 0 is equal to D sub A plus U sub A, which is equal to A. And gamma of 1 is just equal to D sub A. So this path gamma, it joins A, and notice that every element of gamma, so we're just scaling this upper triangular part by 1 minus T, right? The diagonal entries are not changed at all. So therefore, every element of gamma is inside, every gamma of T is inside U, this upper triangular matrix. So this path gamma, it joins A with this dA. dA is a diagonal matrix, right? So dA is this diagonal matrix. So now this diagonal matrix, we will join it to an element of S. So that's easy. So what do we do? So we define a map from 0, 1 to the set of diagonal matrices. D is the space of diagonal matrices in J now. Right. So what do? We take T and send it to the diagonal matrix. So let me just write the ith entry. So 1 minus T. So let's say these entries are D sub A is equal to A11, A22 to AN, right? All these AIIs are non-zero. So 1 minus T into AII plus T times AII by absolute value of AI. Okay. Right. So what is this doing? So at T equal to 0, so let's look at this entry. So let's look at this entry, 1 minus T times AII plus T times AII. Now AIIs are non-zero, so therefore this is always equal to, there's either plus 1 or minus 1. If AII is positive, then this is plus 1. And if AII is negative, then this is minus 1. So what this does is, so suppose AII is positive. So we have 1 here, and AII could be here. So this path, it joins AII to 1. Okay. And if AII is here, so this path, it joins AII to 1. Okay. So similarly, if AII is negative, so then AII could be here. This path, it joins. So the important thing is this path, it never hits 0. So that's an easy check which you can do. And therefore, yeah, this gamma of T, for each T, gamma of T, it's the entries are always non-zero, right? And therefore, so okay, let me call this gamma 2. Let me call this gamma 1. So then we have gamma 2 is a path which joins D sub A to this element in S. This element which is inside S. So this implies that every element A in U can be joined to an element in S by a path which is completely in. Okay. So the next step, so this proves the first part. So the next step that we need to show is that no two elements of S can be joined by a path in U. So step 2 is no two elements of S can be joined by okay. So this step is easy. So let's try to prove this by a contradiction. So if not, so assume that there's a path from 0, 1 to U, gamma, such that uh, gamma of 0 and gamma of 1 belong to S, and gamma of 0 is not equal to gamma. Okay. So then there will be, now remember what is S? S is diagonal matrices, which all entries plus and minus 1. So since gamma 0 is not equal to gamma of 1, it follows that there exists some I such that gamma 0 of II is not equal to gamma 1 of II. This gamma 0 is a matrix and gamma 1 is a matrix. So their ith entries, there will be some I where they differ. Because if they agree in all i's, then it will mean that gamma 0 is equal to gamma 1, which is not true. Right? So what do we do? So we have this 0, 1 to U. And we just project to the ith coordinate. This is the projection now to ith coordinate. So what do we so actually the projection to the ith coordinate, the image lands inside r minus 0, because we know that none of the diagonal entries, so given any element of U, the diagonal entries have to be non-zero because every element of U is in GL and R. Right? So this will mean that okay. So what does this mean? So this simply, so gamma 0 II, we can assume without loss of generality that is equal to 1, and gamma 1 II is equal to 1. So this implies that there is a continuous map from 0, 1 to r minus 0 gamma. So this is, let me call this map projection from post-normal, such that, can I take one more? Yeah. So let me call this gamma prime is equal to 1, and gamma prime of 1 is equal to minus 1. But this is clearly not possible. There is no path which connects minus 1 to 1. So there's a contradiction. So what does this mean? So we have S, we have the set S, and this is two path components. So given an element X in S, we can send it to the path component of U containing X. Yeah. So then step 1, prove that this map is surjective. This map is surjective. Right. And step 2, prove that no two elements of S go to the same path component. This map is 1. Right? So this implies that this map is actually a projection. So we will stop here. And there's a question which I want to address. Okay. So I have to stop now. So maybe other questions that you have, you could ask in the phone. So thank you. Sorry about this. Maybe stop.